Okay, just getting back here after break. Doesn't look like there's any questions to follow up on, so we'll continue along here. If we go back and look at our primary axis settings here, right now I've set the primary back to unlimited. By unlimited, what we mean is greater than 360 degrees plus or minus. So it's allowed to wind up. And I've also made sure not to set the P AUG and S AUG output settings yet. So those are the settings we've got. And if we look at this second project curves toolpath, I've projected down this arc, and if we back plot it, you can see that it starts over here on the right and it moves counterclockwise around the sphere. And we always want to do a test like this. Remember, we've already done a circle with a cylinder, and we do that so that we can make sure that our 0 point is set correctly. 0 point, I mean primary axis 1, 0, and primary axis 2, 0. Because here's what we want. Okay, this is cutting a full circle. And if I post it, you can see that we're starting at C0. We've moved B positive to 44.64 degrees. And as we make the cut, we're now cutting C negative. And this is what we want to see, is that basically, because we've got a B axis, we were able to simply rotate B into the correct position. We haven't moved C. C has stayed at 0. Now, if our 0 was in the wrong spot, and by wrong, right now it's at positive vec x. Because there are 4 directions it can be, positive vec x, positive vec y, negative vec x, and negative vec y, if these settings are rotated, we'll see that in the output. So if I do negative vec x here, so this is negative vec x rotating towards negative vec y, and we post out that same toolpath, it's essentially the same. Okay, starts at C0, goes B44, but now the B winds up, or C winds up positive instead of going negative. Now, if we make a change here, and we say it's positive vec y, rotating towards positive vec x, we'll see it in the output. This is where we have to rotate C90 positive or negative in order to get our B axis into position. And so that's what we want to try and avoid when we're setting up the machine. But in order to do that, we also have to make sure that our geometry is set up correctly. So my toolpath itself starts on the positive x axis. this is the correct starting point for something that rotates about Y, that has a B. If we were setting up a C on A machine, I would want to take my geometry and rotate it 90 degrees so that I was aligned with the Y instead of with the X axis. So let's change this back. Okay, so we're going to go back to positive vec X is the 0, rotating towards negative vec Y as the positive direction. We save it, and that means that this toolpath rotating this way, if we go and we check it on the machine, should be negative. So if we go and we check that on the machine and that direction is actually positive, then we have to reverse this. Okay, so if we need to reverse the sign of the axis, we reverse the sign of the rotary direction variable. So make a negative positive or a positive negative. We always want to test this first and make sure that our starting point is in the right position. Okay, so now we're going counterclockwise, but we're winding up positive. We go all the way around to 360, and then we retract. So when we have an axis that has less than 360 degrees of motion in one direction, then we have to be a little bit more careful about how we plan out our toolpath. Because if this is the start at 0, and I only have 200 degrees of travel, I am not going to be able to complete a full circle. I am going to need to start at either plus or minus 180 on my C-axis in order to be able to make the full cut. So now that we know that we've got our directions and our 0 points set up, because we've done a full 360 degree rotation, now we can go and we can limit the primary here. So plus or minus 200. And I'm going to go plus and minus 199.5 for the intermediate angles here. So now we have a situation as well where the secondary is also going to limit what we can hit if these are our real numbers. And the reason it's going to limit us is because this position in our code is like 44 degrees. Well, that positive 44 degrees is only available to us in our positive travel range. Because right now, negative 30 the other way is the limit. So we can't go to negative 44.64. So now what we try is the same thing, but now we've got these modified travel limits. Okay, so we start at C0, B44, and we get that. So basically we hit our 200 degrees. Next move can't go beyond 200. So we retract, we position to negative 160, and we continue the cut. And right now, going in the direction we're going is winding the axis up. So we may run into a situation, depending on what we leave down here for our secondary, where we just can't hit a full 360 degrees of rotation, but let's try it. Because what's going to happen is if we try to go negative, it's not going to let us. I'm going to do this. Let's put in the real. Let's put in the real actual limits here. Low limit, so that's going to be negative. And this one's going to be negative there. 95 and positive 95. Okay. So now what we do is we go try to give it a bias. We go into the miscellaneous values and we go to the initial primary and we try to pre-wind the head. This is what's known as a pre-wind move. So we're passing an instruction to the post to attempt to position at the start to that angle. And so now what happens is we're going negative. So we go minus 180, we go B negative 44. We should try it with the limits to see if it'll force it to go positive. It may not work. It may be that we have to go positive 180 instead of negative 180 with our limits. So let's see what happens if we go the other way. Well, first of all, let's continue looking here. So we start negative 180 and we go down. We go down, 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 down. But what I'm looking for is what happens when we cross over. And specifically what I'm looking for is, does it just cross over and keep on going, or do we get something funky where it tries to flip the secondary axis on us? Because sometimes that'll happen in the code without retracting. You have to be a little bit careful about how you're setting this all up. What you don't want is for it to go from minus 44 to positive 44 just randomly while the tip of the tool is still on the part, because it's going to cause big sparks. So here we wind up to 180, and we've successfully made the cut. Okay, so we'll leave the limits that we had, and we'll try 180. Error. Tool cannot be positioned within the machine rotary limits. So at minus 180, we couldn't do it. But it may let us do it if we go positive. So now we try positive 180, regen the path, repost. No, still won't let us do it. Because we're being forced to go negative over here. Now, that there may be a situation where we can take the geometry and reverse it. So if we rotate this, sometimes by flipping over where the start point is, it'll let us go the opposite way. And the other thing that we could do is we could change the direction, the positive direction of rotation for the secondary, and see if that will let us fit it. So now if we post out this toolpath again, because of where our start point was, because of the angle of rotation, we were able to do this successfully. So this is a case where, with these limits, it is still possible to cut a 360-degree arc on this sphere. But we couldn't do it with our start point on the opposite side. It just, mathematically, it didn't allow us to get in the real travel range for the machine. If we had kept that same start point, we could have tried reversing the direction, and that may have let us get in there. But the question is, what works on the real machine? On the real machine, if this side really is B45 positive, then we can't hit negative over here. It just won't reach. So that means we have to approach it from this side, and all of our start points for our paths should be on that side as well. But we're only going to see that limitation when we have a machine like this where we are more limited not only for the primary travel, but the secondary as well. Okay, there's only one section where this thing can hit, anything above 30 degrees. And our simple little example here, it's 44, so it's out of that axis, it's out of that travel range. On the other side, it just can't get there. And again, this is one of those situations where if you're not aware of how it's set up and your primary and secondary vectors are not set up correctly, it can really screw you up if you jump ahead and start putting in all your limits first. Because again, without knowing that your vectors are set up correctly, this thing is it's just a math powerhouse. All it does is do a bunch of vector math and calculate angles and spit out a rotary address. It doesn't care about A, B, or C. Those are just letters to it. What it cares about is primary and secondary, and where is the 0 point, and which way is the positive direction of travel. And once we establish that, then it applies the limits and tells you whether or not, the path that you're creating will fit mathematically inside those limits. Okay. So we'll go back to 5-axis generic. Okay, so we've talked about the rotary limits and the rotary limit types. Basically, we don't need to worry about setting rotary limit types because rotary limit types are set for us automatically by this variable here. So once we set the rotary limit values, so there is another option inside the post as a variable. The variable ADJ2SEC stands for adjust to secondary. The purpose of this post switch is to allow the secondary axis limit to exercise control over the primary axis. By default, the post attempts to avoid large primary axis moves. When the secondary limit is tripped, the post attempts to reposition the primary axis. The primary axis is repositioned within a 180-degree move, and the secondary axis is checked to see if it is within the limits. There is this guy right here. So there are a couple settings zeros off. 1, use method when secondary is out of limit. Use with primary limb type equals 1 to keep the secondary. Use with primary limb type 1 to keep the secondary as the controlling limit when the limit is tripped. Use with primary limb type 2 to allow a 180-degree reposition. And what they're talking about is these guys right here, primary limb type and secondary limb type. So these will auto-magically get set, automatically, but I call it auto-magic, by this variable here, auto set limb. So we really, I mean, you can go in and set them, but if you do that, you should turn off the auto set limit. So in this case, primary limb type would be 2, and secondary limb type with these values is 0, less than 180 degrees. This adjust to secondary really comes up more on Trunnion style machines, where we want to allow that secondary axis of the Trunnion to exert a greater influence over the primary axis. There are some additional settings that apply to both types, well, I should say all types of machines, both table-table, head-table, and head-head. There are 2 sets of rotary axis offset values. So the rotary axis offset variables hold the distance that the primary and secondary axis of rotation are offset. They have different meanings based on the machine type selected. So these are known as the shift axis variables, S axis X, which, by the way, if you try to say that 10 times fast, is a real tongue twister. S axis Y and S axis Z. In addition, there's another set of 3 shift variables that are typically used with the Nutating style machine, and these are N underscore S axis X, N underscore S axis Y, and N underscore S axis Z. If we look in the post at the shift variables, there's some additional notes that are important to kind of read and be aware of. Axis shift. There is a switch in here, shift misc R, SHFT underscore MISC underscore R, which tells the post whether we want to read the axis shift values from the miscellaneous real numbers. This is for an option that I would consider, I guess, on production type jobs where you need to be able to tweak the blending of 5-axis cuts together. And what that allows you to do is put in some XYZ shift values in miscellaneous real 7, 8, and 9. Now, they don't tell you really hardly anywhere that it is MISC reel 7, 8, and 9 for X, Y, and Z, but they're there. Because the default is to turn this off. And what this allows you to do is shift the path left or right in X, front to back in Y, and up and down in Z. So you can apply this shift value on a per toolpath basis to allow you to to perform a global shift like you were at the machine. So this would be similar to like a G52 shift, where you just want to tweak the path a little bit, front to back, left to right, or up and down. Now, by default, that is not on, and so what we are left to is these other sets of values. So parts programmed where machine 0 location is the WCS origin. Applied to the spindle direction independent of the right angle head. So this will shift just the spindle direction along the spindle axis of the machine, not the spindle axis of the right angle head if you're using one. For table machines, offset of the tables to the secondary axis relative to the machine base. So what we're talking about here is this is typically used on a table style machine where the axis of rotation on your primary has a shift relative to the secondary axis of rotation. Now, if we're looking, for example, go back to an easy picture here. Let's take this Haas VFTR table. So this is probably a TR160 or a TR210 table. And when we're looking at it, we have this A-axis center line for the machine. Now, they happen to be dumb and they label their platter a B-axis. Forgive them, Lord, they know not what they do. Okay, so there is typically about 125 thousandths of an inch shift between the center line of the A-axis and the height of this platter on the machine. So when you rotate up to a -90, that face will be about a quarter or an eighth of an inch away from the center line. And when you rotate the opposite direction, it's an eighth off in the opposite way. And in addition, there will typically be a slight offset in Y. So, you know, they don't build these things exactly perfect. So, you know, you might have up to, so in some cases up to 1,000. Usually it's about, 3 to 6 tenths plus or minus in terms of, how these things rotate relative to each other on the machine. And so what this allows us to do in the post is input those numbers and allow the machine to compensate. So on a Haas machine, for example, and we're using inch values, we might have something like this. There's going to be some shift that's close to an eighth of an inch. Okay, somewhere close. And depending on how this is set up, again, we're setting this up for a gantry style machine. When we get to doing the trunnion, we'll go through this example. But if it was rotating about X, then we would probably have a slight shift in Y. If it was rotating about Y, we'd have a slight shift in X. And there's procedures that we can go through on the machine to measure the machine and figure out where our center of rotation is and what those values are. So I'll do a quick plug real quick. One of my favorite things about this book by Carlo Apro is that he gives us in pretty clear detail procedures for measuring the machine and determining these shift values. So, know your machine. Common multi-axis machine configurations. Table multi-axis machines. Machine rotary zero position. Nesting positions. All this different stuff about figuring out the machines. Indexing, machine simulation, selecting the right machine, CAD CAM, boom, boom, boom. And I don't know if it'll show it to us in this little preview here, but he goes through the procedures of using, so we're getting back to the index, of using a test indicator and figuring out where your rotary positions are. So, when we input these shift values, it allows the post to understand that there is this offset from the center of rotation, and to take that offset into account as we start to rotate the secondary. So when we rotate the secondary at 45 degrees, it's going to offset by, the sine of 45 for whichever one of these has the shift value to shift our coordinates into the right position. This other set, nutating shift axis. Oh, by the way, up here, offset of tables to secondary axis relative to the machine base. For tilt head table and head machines, the part is programmed at machine zero location. So we can offset in the head based on the secondary axis relative to the machine base. But normally for both tilt head table and head machines, normally we use the tool length for the offset in the tool direction. Okay, so this is a note saying normally this is for table. These guys right here. So don't try to use those for tilt head table or head style machines. Use the tool length instead. Now there's one other set of values that could be used. The nutating values here are normally for the nutating machine, nutating axis shift, used when calculations are based on on M type 3 or greater. However, top map and tool plane paths use the axis shift above. They use these values. 5 axis use these. So if you're programming a full 5-axis path, the full 5-axis path uses the nutating shift values, not the S-axis values. So if you put some shifts in here and you run a 5-axis path, you're not going to see any shift occur. And what this really allows you to do is it gives you a choice. When you're programming 5-axis on a table machine, you can shift the 5-axis path using these nutating values here, or you can turn on Shift MISC R and you can shift the path using these 3 here. 7, 8, and 9. So really it's up to you, but it's important to know that these values are applied to the 5-axis, these values are not. This is only used for tool plane work and when we're doing top map, which is tilted work plane. Okay. All of the 5-axis paths on a table machine use the N shift axis values, unless you've got shift misc R turned on. And in that case, if you're using shift misc R, you're going to input the values here. Now it depends on your machine type as well. So getting back into the post, this is typically only used for table machines. Okay, but all of the 5-axis paths are going to use the N shift values, or they're going to use the misc real values depending on your setting here. So by default, when this is set to 0, shift misc R, not R intersect. When shift misc R is set from 0, we always read for 5-axis the shift here on a table machine. Okay. All right, let's see where we're at here. There's another switch, R_intersect. So the rotary axis offset for table and tilt head table can have two interpretations, where the program 0 point is located relative to the offset axis. This is a user preference, and the variable must reflect the user's preference. The selection is ignored if the axes have no offset. This is talking about this guy right here. So what we're talking about with this R_intersect variable, R_intersect set to 0 directs the post to calculate output with the machine coordinate at the part 0. Part/machine 0. So we're showing the part 0 point here. The offset distance is from the machine 0 to the secondary axis centerline. So the part 0 can be set at the face of the primary axis table. R_intersect set to 1 directs the post to calculate output with the machine coordinate origin at the secondary axis centerline, the machine 0. The offset distance is from the machine 0 to the origin of the part as drawn, part 0. Coordinates are relative to the machine 0 as the secondary axis turns around the part. And honestly, it's been so long since I messed with the R_intersect that we'll have to set up a demo when we actually get to configuring a Trunnion machine. Basically, I think it has to do with whether or not we put the 0 at, whether we program with the 0 as it is on the machine, or whether we program with the 0 point on the part. Normally when we're programming a 5-axis part on a table machine, we have to offset the part in space relative to where the center line is. And I believe this switch allows us to get away with not doing that. So we can actually put the intersection of the origin on the work offset to the part itself. But then in order to do that, we have to put in the real numbers here for the shift axis from the work coordinate down to where the center of rotation is on our machine. Normally we recommend people don't do that, and they just because quite often you're going to end up otherwise you have to end up setting and maintaining the shift values inside the post for every new part. So basically you're going to have one post for each part if those values are changing here. That's why I recommend people set the post up where the center of rotation is your WCS origin, and you build your fixture and part holding as it exists in the real world. That way the shift can account for just the misalignment of the rotary axes instead of the full offset of this distance from the part 0 down to the axis center line. And I hate this example too, because they show this example S axis Z minus 100, and then they show this one here, which is like the same frickin' numbers. So you start looking at it going, well, that doesn't make any sense. Basically, do you want to program with the center line of rotation being known in Mastercam, or do you just want to program from a 0 point on the part and have the post figure it out? Again, the problem being that you end up having to manipulate these values on a per part basis. So it'd be a neat feature if there was a better way to pass that data along, I suppose. Okay. Well, we're just about caught up on where I wanted to be. Do the post flag later. And we'll get into talking about the feed rate stuff a little later. Yeah, all the stuff we're going to get to. So, I think we'll go ahead and open it up for questions tonight. And see if we can answer a few questions, then we'll wrap it up. I guess kind of on time. Yeah, little on time for once. Yeah, do you want to ask it in person, Mike? Do you want me to unmute you? You got a mic? Let's see if you do. No. Okay. Yeah, no worries. Just go ahead and yeah, ask your question, please. Okay, well, while Mike is typing out his question, Nick's got a question. would it be possible to unhook the MISC reels for axis shift and use them with, say, G52 in the program? Probably not. And well, it depends on what you wanted to do with the G52 shift is the real answer for that. Because the place where we pick up the shift MISC R settings is inside P shift MISC R, and this gets called from within. Yeah, this gets called from within the PSB file. What we end up doing is looking at the shift MISC R variable. We say, hey, if cut type and top map and previous M type is greater than 2, we set the nutating shift variables, and then we update them so that the previous and the current have the same value. If we're not, if we're in tool plane mode or we're not in top map and stuff, then we end up setting the shift values down here. If the shift values are 0, so in other words, shift MISC R, if we turn that off inside the post, this never gets read, these never get set. So at that point, you can use MR7, MR8, and MR9 for whatever you want to do with them, as long as you don't turn on shift MISC R. So the answer is you could use those for G52 shift if you wanted to, as long as you make sure that shift MISC R is set to 0. And then MISC so in the 5-axis post, there are two predefined post blocks, P-MISC int, P-MISC real, and you could certainly capture your, you could do something like this. But you just have to remember not to turn on the shift MISC real setting. Okay. So yeah, you could certainly use the values in that way. Yeah, I saw that. Let me get back to that. So Mike says, I've never had to shift in X or Y, but the center of A is 5 thousandths above the platter on one of my machines. I've always just set my WCS to 5 thousandths above the platter. What is the difference between doing that and setting S axis Z? The difference between doing that has to do with the setting that we looked at and what happens when the part rotates. So when the part rotates, do we apply the shift or not? So I'll tell you what, we'll get to see that when we go through and we set up your Trunnion, because we were taking a look at that on the when we were in our office hours. So we've already got started on that, and we'll just go ahead and continue on that. Well, actually, when we start with the Trunnion on Thursday, we're going to start from scratch, and we're going to lay out the whole Trunnion. But we'll go through and we'll test it, and I'll show you what the difference is. So really, we have to make sure that the shift settings in the post match the way that we're setting up the job in Mastercam. Now, normally I recommend you do it just like you've been doing that, which is set your WCS origin 5 thousandths above the platter and program everything there, and it all works out. Really, again, the shift value to me should account for any error or misalignment on the machine itself, and we should just be able to, program it as if the center line were in the exact center line, and then the post will offset for us. So yeah, we'll take a look at that, and I'll show you the difference when we do our 5-axis trunnion setup. Now, when we start looking at the setup of different machines, last thing I'll mention for tonight, and you go to your generic 5-axis generic post PDF, if we scroll past all of the miscellaneous integers and real stuff and go past this little stuff on post customization, there are some slides that show you some setups for typical machine types. So here we go with some various type of 5-axis machines in the real world. Rotary table on Trunnion table. So this is showing us a table with an A, primary C, secondary A. And it takes you through the settings here. So primary is C, secondary is A, P AUG and S AUG output are set to 0. M type is 0. This is VEC Y rotating towards VEC X. And rotary axis 2 is VEC Z rotating towards VEC Y. Primary is unlimited. And secondary is plus or minus 90. So these are the basic settings for an A on C rotary trunnion table. Here's a Fadal where we've got a rotary B on A, or actually A on B. This would be A is the primary, B is the secondary. And here's one where I believe with B, this is like the 0 position. So P AUG and S AUG are set to 1. I think this should actually be B. I think this is a typo right here. Primary is A, secondary is B. M type is 0. The primary, VEC Z rotated towards VEC Y. And then VEC Z rotated towards negative VEC X for the secondary. You can see the primary is unlimited. The secondary is 0 to 110 with an intermediate at 0 to 90. Here's a tilt head. B on the machine, A on the spindle. And here you can see pivot length, use overall length on the tool definition page. So this is an A on B. So primary is B, secondary is A, M type is 2, VEC Z to VEC X on rotary 1, rotary 2 is VEC Z to negative VEC Y. Use tool length is 1. Tool length is set to, actually 1 is overall length. So Shift Z pivot, Shift Z by tool length. Primary plus or minus 120, and the secondary is minus 90 plus 30. Here's another C on A. So again, settings for the C on A. Here's a B tilt head table. So one axis is on the table, one axis is on the tilt head. This is a B on the head, A on the table, and it gives you the settings there. Here's C or B on the table, A on the spindle. So for a Cincy, here's a Nutator, C on B. All right. So more stuff to cover on Thursday for sure, but I think we're going to wrap up for today unless there are any final questions. Good. Okay. All right. Well, let's go ahead and wrap up, and we will continue starting on Thursday configuring a Trunnion. So we're going to start from scratch, configure a Trunnion, and go through the basic setup for that. And, you know, basic, similar, simple test scenario where we put down a couple of drill toolpaths, a couple of 5-axis toolpaths, and make sure that the primary and secondary are defined correctly. Then we set our travel limits. Then we, you know, do the final tweaking on the post. So, all right. Well, thanks everybody, and don't see any final questions. So let's go ahead and wrap it up. Gonna shut down the broadcast.